includes speed of the wave, wavelength, that's how you spell wavelength, and frequency. What is the formula that we use for working with waves? Anybody? Don't make me pick on you because I will. What about Brianna? You're unmuted. What's happening, Brianna? No? Okay, that's okay. You can be shy.
So how about, let's be a little bit more specific. What is the equation for the speed of light for waves?
Yeah,
isn't it lambda times nu?
Okay, lambda times nu equals what?
Equals the speed of light, c.
C, yes, exactly. And what is the speed of light, sir, if you are so kind as to tell us?
Isn't it 3 times 10 to the 8th meters per second?
Yes, it is indeed. You may see it written as 3.00. That's just for sig figs, right? So that has how many sig figs?
That has 3 sig figs.
Yes, 3 sig figs. Okay. So this one we already said was wavelength, right? That's lambda. What is this funky looking V here?
Frequency.
Nu?
Yes, it is nu, and I heard somebody else say it is frequency. Indeed it is, sir. Frequency. I hope the chat is answers. What is the units for frequency?
Hertz.
Hertz. What is the conversion factor for hertz, though? Anybody know?
Isn't it like 1/seconds or something like that?
Yes, it is. I'm proud of you guys. Yes. So when you guys are working out these problems, your speed should always be in meters per second, right? Because those are the units of speed. And then wavelength is in meters. And your frequency is going to be, for purposes of canceling out units, is going to be 1/seconds. But when you give out your final answer, you want to write it as hertz. Yes? Any questions? Comments, concerns, panic, confusion, anything at all?
No.
Awesome. Okay. So hold on, before we move on, I'd like to see if you guys can see this like conceptually. If I were to draw a wave as like that, right, on an XY plane, can anybody tell me, or can anybody draw on the whiteboard, because you should be able to draw on the whiteboard, can anybody draw how we measure the wavelength and the frequency? Or can anybody tell me where to draw it? Is it in the chat? Is that what's happening in the chat?
Jonathan was just talking about which wavelengths correspond to which color.
Oh, okay. Anybody want to take a wild guess before I tell you what it is?
Is it in the second peak? In the second,
What is in the second peak?
like from the beginning to the top of the second, like little peak.
From here to here?
No, like the top one.
So from here to here?
The right one. To the right side?
This one?
No, right side.
Oh, this one. Oh, okay.
Over here?
Not me being dyslexic. From here to here? Like that?
Yeah, I believe so.
What is that?
That's the wavelength.
Yes, you are 100% correct. That is the wavelength. What about the frequency? Let me switch colors. Thanks, Corina. What about the frequency? How do we count frequency?
From the highest point and the lowest?
So that actually, from here to here, that's actually called amplitude. And we don't really work with it, and it's actually up to the x-axis. And we don't work with that in chemistry. That's more of a physics thing.
Okay, guys.
Isn't it from one peak, from the top of one peak to the top of the next peak?
Yeah, from here to here to here to here to here, right? Another way you can measure it is through the x-axis. Every time it passes the x-axis, you're just counting how many times through a certain point the wave is traveling. Yes, and that's your frequency, and that's how you know how many waves you actually have. Yes?
Yes.
Yes? Okay, awesome. Corina, you were gonna say something.
No, I wasn't. Don't worry.
Okay. Okay, everyone good? Can I switch the whiteboard? Okay,
Yes.
3, 2, 1, we're going. All right. Okay, now let's talk about the equation with Planck's constant. Planck's constant. What's the equation that we use with Planck's constant?
So is it E equals HV?
Yes, it is. What does the E stand for?
Energy.
Doesn't it stand for energy?
Yes, it does. And what is H?
That's Planck's
Planck's
constant.
constant.
Yes, indeed. And what is Planck's constant's value?
6.63 times 10 to the negative 34.
Negative 34.
What
are
do
the
you
units
guys-
for this?
Joules times seconds, I think, is what it is.
Yes. Okay, now this is a negative exponent on the 10 times the whatever, right? So is this a really big number or a really small number?
Really small number.
Yeah, it's a really, really small number. So be careful when you are memorizing this for the test, right? That you have a negative exponent because you want it to be a small number. Yes? Okay. And this guy, we already identified it earlier, but for laugh and giggles, what is this? What is this fancy looking V here?
Frequency.
Ooh, I'm going to jump in here. But what specifically is the energy measuring? It's the energy of what specific, I guess, thing, what we're talking about.
Entity.
Electromagnetic waves?
Okay, that's
Yes.
it's the energy of what comes from those electromagnetic waves, or what produces those electromagnetic waves.
What makes these?
It rhymes with proton.
Yeah, photon.
Photon.
Yes.
So make sure, this was one thing that tripped me up when I was taking this course, but when you have E, make sure it's just one photon. So when you're talking about a mole of products or a mole of photons, you have to do the according calculations and conversions.
Unless it's asking you for the energy of all the photons, like the mole of the photons, then you're fine. But if it asks you for one photon, you have to be careful, right? Okay, yes, the energy of one photon. Because what does an atom look like? What does an atom look like? Is it just like square?
Well, it has a nucleus with protons and neutrons,
Yeah.
and then it has
protons.
fields of electrons around it.
Yeah, right. And it comes in different energy levels, right? These are where the electrons are. So what happens in an atom when we produce one photon, when we release one photon?
Is it light? It produces light.
How do we do it though? How do we produce light?
Isn't it the electrons moving from one energy level to another?
Yes. In what direction?
They would be losing energy when the light's emitted.
Okay, they're losing energy, so that means
It's becoming more positive, or
well, not exactly. It doesn't have to do with its charge. If we have, okay, let's do another circle because we can. Let's say we have an electron in this shell, right? To produce a photon, does it have to go up in energy level or down in energy level?
Up.
Up? Why? So we said that the electron has to lose energy to produce light. Yes?
Yeah, so it's moving from an outer shell to an inner shell.
To an inner shell, right? So it's moving down an electron shell, because in order to move up an energy level, you need more energy, right? It's more work to go up the stairs than down the stairs. Yes? So when we're producing a photon, we're going down an energy level 9 out of 10 times instead of the outermost shell, but I drew it in the middle just so you could have options to pick from. Yes? So every time an electron goes down an energy level, we're producing one photon. And depending on its energy, which is this equation right here, that's the color of visible light that we see. Yes? Yes, no, maybe so?
Are y'all like 100% sure that you know what a photon is? Because this is important.
Yes.
So when you release energy, you have a photon?
Ooh,
Yes.
Can I try explaining this one?
Yeah, go for it, Jonathan. Go for it. Take control.
Love explaining photons. So we know the conservation of matter, energy, and all that stuff, right? So the conservation of matter and energy basically says that matter or energy cannot be created or destroyed, only transferred, right? So when we have we'll say an atom, right? And what happens if we add energy to the atom, right? It just can't magically have energy. We have to add energy to this. And if you were in lab, you would have seen something that's like the flame test, where you just put it over a flame and see what color it burns. So when we're talking about this one, and specifically when we're talking about atoms, whenever we add energy to this, the energy doesn't go to the nucleus. It goes onto these electrons. And what happens to those electrons when we add energies is it jumps up shells, or those energy levels. Right, so when it goes up to this energy level, it's compensating for we'll put like X amount of energy that we put. We put X joules to this atom, and it causes the electrons to jump up in an energy shell. But remember, electrons don't want to be in this excited state. It doesn't want to be energized, right? So it's gonna somehow find a way to move that electron back to where it's supposed to be. But remember how we said that energy cannot be created or destroyed. So when that electron drops down to that lower energy level, it's going to emit something that we call the photon. And that photon is really that extra energy that the atom emitted. Does that make sense? So yeah, so whenever you're adding energy and that's like heating up or, doing whatever you need to do, in this case, it's most likely you're going to see it as heating up in your exams and all that stuff. But you're just adding energy to the atom, and it's causing those electrons to jump those energy levels, and it doesn't want to do that. So it releases that photon in order to be, I guess, calmed down, to be chilled, just to be vibing, and that's what we call the photon.
Just to add on to what Jonathan said, just super quick, that's why we're able to see color and things like that. And I don't know if you guys have seen like pictures of like things that are like in infrared or X-ray or anything like that, but all that's happening like instantaneously with all these atoms and stuff like that. That's why we can see color, and there are other things that we can't see because it's all on different wavelengths being bounced off.
Any leftover questions from what Jonathan said or what Jeremiah said? We're good? Yes? Guys, what's new?
I'm done.
Oh, come on, don't kill my favorite joke. What's new?
Well, it's frequency.
Okay, yes. But what is it? What's the the mathematical way to solve for new?
What's the symbol? Sorry. How do you solve for new? What's new?
Well, it's the speed of light divided by the wavelength.
Yeah, that's not the joke, but yes. You're not wrong.
That's not. We were trying to make a joke, but that's fine. Don't worry.
But yes, it's okay. It's C over lambda, right? What's new? C over lambda. Okay. Anyway, let's move on. Now let's do. Any questions about this? Anything at all? Everyone's good?
I'd say let's do a couple problems where they deal with the moles of photons.
Okay, bet. Who wants to do that? I don't have any handy.
I have one if you like.
Yeah, go for it.
Okay. Give me one moment. I need to pull it up real quick. Actually, this one was in your module. So it'll make it a bit easier. Oy. Give me one moment. I need to move some stuff. Okay. So this one is in module 10, obviously, but it's in your workbook and it is problem 3. Okay. Close chat and then I'm gonna annotate. Okay. So for this problem, we are given that the frequency of the light of a wave with this problem we're told that we want to find out what the frequency is. And we have a light of a wave and it has a wavelength of 585 nanometers. And then we are also asked, yes, thank you. And we are also asked, what is the energy of a mole of photons with a wavelength of 585 nanometers? So we're looking for the energy, but what's the one main given in that problem? What the energy of what? Ow, I hit my leg. What are we looking for? The energy of one photon?
Energy of a mole of photons.
Yes. So we're gonna have to do some extra math at the end. So 1 mole of photons. Okay. First of all, how do I find my wavelength, my frequency?
So you're going to use the equation V equals C over the little wave thing.
Over my wavelength. C over lambda. And then what's my C?
Like 3 times 8, 3 times 10 to the 8.
3 times 10 to the 8th. And what's my unit?
Is it ms to negative 1?
Meters per second, yes.
Yes.
Yeah, meters per second. That's a strange way of putting meters per second, but yes, ms minus 1, it works. Okay.
That's how they type it up, but yes, you're not wrong.
Okay, and then what's one thing you guys already noticed about my units that I need to do?
You need to convert to meters?
I need to convert this into meters. So 585 nanometers. Is nanometers larger or smaller than meters?
Smaller than meters.
Smaller than meters. Get a small number. How do I convert?
So isn't 1 nanometer 10 to the minus 9th meters?
If we're going, yes, if we're doing 1 nanometer, then it would be 1 times 10 to the minus 9th meters. So what do we get? What number do we end up getting once we calculate it?
Is it 5.85 times 10 to the negative 7 meters?
Yes, 5.85 times 10 to the negative 7 meters. Okay. So do I have all the necessary variables in order to solve for my frequency?
Yes.
I believe so, yes.
Yes, we do. Because we have our speed of light and we have our wavelength and the correct units as well. So when we solve it out, let's go ahead and plug it in. 8 meters per second. And then here we have 5.85 times 10 to the negative 7 meters. All right, what ends up happening to our units?
Well, the meters cancel out.
Mm-hmm. And the
So
seconds?
you're left with per second, which is hertz.
Mm-hmm. We are left with 1 over a second. So that's how we know we end up with the correct unit. And then what frequency do we end up getting?
Point 13 times 10 to the 14th.
Sorry, I think I think it cut off right when you said 5. So yeah, 5.13 times 10 to the 14 hertz. Okay, and that is correct. Nice. Okay, now how do I calculate my energy? What equation do I have to use that?
Frequency times wavelength.
Not frequency times wavelength.
At frequency times the Planck's constant?
Yes, times Planck's constant. Let me go ahead and make that look like an H. Okay, and then what's Planck's constant again?
6.63 times 10 to the negative 34 joules times seconds.
Mm-hmm. Sure, and that is correct. Oh, so it looks like seconds. It's joules per second. Okay, and then do I already have all the necessary variables to solve for my energy?
Well, if you use the energy equation now, you only be solving for 1 photon.
Mm-hmm. Yes, that's one major thing. We're solving for 1 photon. We'll get to that part right now. Let's calculate our energy first. So let's calculate our energy. So if I have my energy is equal to 6.63 times 10 to the negative 34 joules per second. And then our new frequency is 5.13 times 10 to the 14, 1 over a second. So am I left with joules at the end once I perform my calculation?
Yes.
Mm-hmm. Mm-hmm. Yes, I'm left out with joules only. So what energy do we get?
I got 3.40 times 10 to the negative 19 joules.
Mm-hmm. 3.40 times 10 to the negative 19 joules. Okay, and you already said this is for 1 photon. So I'm going to rewrite this over here, actually. So I'm going to rewrite it as 3.4 times 10 to the negative 19 joules per photon. How do you guys think we can convert this to a mole of photons?
Multiply by Avogadro's number?
Yes, we would multiply by Avogadro's number. So let's multiply by Avogadro. So 6.022 times 10 to the 24th photons in 1 mole of photons. So what energy do we get?
Hey, Diego, isn't Avogadro's number times 10 to the 23rd rather than 10 to the 24th?
Oh, sure, yeah, sorry. Sorry, I have it wrong in my notes. Oh, sorry, I wrote it wrong. Yes, thank you.
Yes, taught on top of everything today.
So what energy do we end up getting?
I got 2.04 times 10 to the fifth.
Yep, that is
I'm not
correct.
sure if I'm correct.
Yeah, that is correct. 2.04. Oh, sorry, it's 4. Not 2.04 times 10 to the fifth joules. 1 mole. There you go. Is there any questions? How does everyone feel about waves so far?
I have a question, and it's for the students.
Oh. All right.
All right, so I put on the chat, what color is this light? Obviously, Jeremiah and Sophia, they tried. Maybe a student can help us out.
If you guys
I'm
don't
sorry,
know,
what was the question again?
What color is the light? Or, yeah, is the light that we're talking about?
Jonathan sent the spectrum in the chat. You just gotta scroll up a little.
All right, good enough. Thank you, Brisa. You do need to, I guess, remember the spectrum, and I put it up on the chat, but you will need to remember it for your test. So this is just good practice to get used to it now.
Any questions on waves?
We're cutting a little short. We should probably move into module 12.
Yeah, we should move to 12.
Okay. I'm going to go ahead and clear the drawing. In 3, 2, 1. Oh, okay. All right, go ahead and clear it. Yeah.
The notes for later.
Oh, okay.
I'll do module 12 then. So module 12 is just periodic trends. And Diego, can you actually let me screen share?
Oh, I got you. Hold on.
So we got 4 periodic trends. What are they?
Oh, wait. Before you screen share, let me save these notes. Hold on.
So we have ionization energy, right? Atomic radius, I guess. And then I'll leave the other 2 for someone else.
All right. So we got atomic radius and ionization energy.
Electronegativity, negativity, and electron affinity.
All right, perfect. All right, sorry. So let's go off with the most important one that I think, like in my opinion, is the most important one. It's electronegativity, right? What is electronegativity?
Isn't it the energy required to get rid of an electron?
Close, but that's electron first ionization. My bad.
Oh, okay.
But it's close. It has to do something with that.
Is it the energy that like an atom has pulling its electrons to the nucleus?
Okay, we can do that. So what electronegativity is we'll say we have element X, right? Element X wants to hold on or give away these electrons, right? And electronegativity is really how strong is it holding on to those electrons, right? It's not the charge. There's no like, you're saying like energies and all that stuff, but it's just how sticky the electrons are to the element. Does that make sense? So think of yourself as a nucleus, right? Think of yourself as a nucleus and think of your phone, right? You keep your phone close to you. And if someone tries to take away your phone from your hand, you kind of try to snatch back, right? So think about it that way, right? So your electronegativity to your phone, imagine you're the atom, is really high. Does that make sense? So electronegativity really is how sticky an atom is, or how hard does it want to keep its electrons. Electron affinity, does anybody know what that is? Well, electron affinity and first ionization energy are sort of the same thing, just reverse, right? So electron affinity is how much energy you need to push in order to force an electron within an atom. And first ionization energy is how much energy you need to input to take it away, right? So think of it as just a forward and reverse type of thing. And then atomic size, well, it's just atomic size, right? Does that make sense to everybody? Okay, cool. So let's go on to the periodic table. And can anybody tell me what the trends are for atomic size?
So it's increasing from right to left.
Increase?
And then from right to left. I don't know, like I say increasing from right to left. I don't know if that's right.
Well, not quite, but let's see if you can get the other one. What happens to it when you go up and down?
It increases.
Yeah, so if you go from up to down, it increases. And actually for this one, it decreases. And we're talking about ground state atoms at this point. So it decreases from, my goodness, you are right. I am sorry. So yeah, to left, I am so sorry about that.
You're fine. I was like, oh, wait, what?
No, I guess I don't know my left and right, but no, that's fine.
The leftover pumpkin pie.
Yeah. So it increases from right to left and up to down. And obviously we know up to down because if we're adding energy levels, it's going to get bigger. And in reality, what happens is atoms kind of look like this, but in reality, it's mostly kind of like that, right? Where you have a small dot in the middle and it's surrounded by electrons, right? And then one thing, I'm not sure if you've heard the pickup line. Biology says you're 70% water. Chemistry says you're 60% oxygen. Physics says you're 99.9% space, but I think you're 100% Q. Technically, that's not wrong about the physics one, where the nucleus on the very, very, very middle is surrounded by mostly 99% space. So the nucleus isn't going to change as much when we're like looking at the different elements. What's really changing is the electron cloud around it. Now, that being said, we know this trend, right to left and then up to down. First, ionization energy. Can anybody tell me what that trend is?
So it increases like when you go from down to like bottom to top, and then it increases from left to right.
Okay, perfect. And then this is the same things for ionization energy and electron. Right, perfect. So that's of ground state atoms. And let's, I guess, focus on, I guess, the relationships between these. And let me do a whiteboard now. You just restart. So let me clear all drawings. Okay, so when we're looking at this, remember how I said that electronegativity is really just how sticky those electrons are to the atom? So that has to deal with the same ionization energies and the other ones, right? Ionization energy and electron affinity, right? So if you're really sticky, right, and if this atom is super sticky, it's not going to want to let go of those electrons super easily, right? And because it's pulling in with a great amount of energy, great amount of force. You guys were correct on that, right? So if it's sticky and these ones have a certain energy, you have to either overcome this energy or match the energy in order to push or pull in. So that's a relationship between electronegativity and electron affinity. Typically, why? Okay, so does that make sense to everybody? So the more electronegative it is, then the higher those energies are going to be.
Can I step in a little bit, Jonathan?
Go ahead.
So I have a different way of thinking of electronegativity. which because electronegativity is mostly about how an atom is pulling on the electrons when they're in a bond. So the trend is, oh, hold on, actually let me share a picture instead. Okay, fine. That all right, fine. I'll just share that. Okay. Let me just share my screen really quick. So for electronegativity, the thing about that is that it's pretty much mostly how it's in relationship to whatever atoms are bonded to it. So this mostly has to do with whether how strongly electrons are pulled by an atom when they're in a bond. So for example, so the trend is, as Jonathan already mentioned. Oh, what's the trend? Since Jonathan already mentioned it, I'm gonna ask you guys, what's the trend for electronegativity?
So from left to right, it's increasing.
Left
and
to
then
right.
from the bottom up, it's increasing as well.
Right. Okay. So then which one? So actually, let's make an example. So let's say, for example, HF. Which element is more electronegative, hydrogen or fluorine?
Fluorine.
Fluorine, right? So what's going to happen with fluorine if it's more electronegative than hydrogen? What's it going to do to the electrons in the bond?
Going to pull them towards it.
It's going to pull it towards them. So even though they are sharing those sharing those electrons, they're not sharing them equally. The fluorine is going to pull those electrons closer to itself. The fluorine is going to pull them closer to themselves, and that makes, what does that make, guys? What's this? What does this arrow show? There's actually a little bit of jumping ahead, but does anybody know what this arrow means?
The dipole.
The dipole, right? So what does it mean when you have a dipole? Oh yeah, yeah, bless you. If you sneeze, bless you. Just like Sophia said.
What happens in a dipole? Who answered dipole?
Somebody answered the dipoles. So
I did. So it's talking about the polarity of a compound.
So it makes the bond polar, right?
Right.
It can be what determines whether a compound is polar or not. So what does that polarity mean? What are those? What does that polarity mean in that case? What does it mean for fluorine if it's pulling the electrons closer to itself?
Not understanding what you're asking. Sorry.
So the dipole. So we talked about a dipole, right? So there's two poles. So that's what it means to have a dipole. Di means two. So that means you have two poles, right? So what kinds of poles do you get? It's like a magnet, right?
What kind of poles does a magnet have?
Yeah, positive and negative.
Positive and negative, right?
Each other, like repellent kind of forces. I don't know.
Well, they're not repelling each other in this case, but Brisa actually, well, I'm looking at what Brisa just mentioned. Is fluorine slightly more negative than hydrogen? Yes, exactly right. Why do you guys think it's more fluorine is more negative than the hydrogen is? Oh, this is actually the wrong symbol. So this is how we draw these dipoles. So why is fluorine more negative than hydrogen? Of course, it's a neutral compound, but there's kind of that dipole kind of makes it more negative towards where fluorine is. But why is that? Again,
because it has more electrons.
have more electrons close to it. Exactly right. So, if it increases from left to right, yeah, it increases from left to right. Yeah, so that's what electronegativity is. So that it's related to it's relative to whatever atoms are bonded to another. So fluorine is, as we've already seen, one of the most electronegative element. And somebody actually asked, oh, that was a quiz from Paulina. So Paulina earlier asked if did Paulina let me know if I'm just being redundant, but did anybody already answered if
Yeah, I don't think
the
anyone
noble
has
gases are included?
Yeah, no one has answered in the chat yet.
Okay.
No, they're not.
No, they're not. Why is that?
Because they're the most stable elements. So they don't have any negativity.
Right. They're not usually very much involved in compounds. I know krypton and xenon, I think they have a little bit of electronegativity because those can actually make some compounds. But mostly we don't really care about the noble gases. So for as far as we're concerned, the most electronegative element is fluorine. So there you go. So actually, yeah, we'll bring electronegativity again later. So I just wanted to point that out because it's not so much whether they're sticky. I think that example fits more for what is it? Electron affinity, I think. But I really like how. Sorry, Jonathan, if it seemed rude. Me butting in.
That's completely.
I'll shut up now.
Now, if you have anything else to say, be completely fine. We're all here. It's a learning experience. Before we had to end in like 8 minutes, I'm going to run through what effective nuclear charge really is. And effective nuclear charge has to do with ions and all that stuff because we have something called isoelectronic ions. And so that means they all have 18 or isoelectronic elements. So that means they have 18 electrons or the same number of electrons, right? So give me a compound that has 18 electrons. Ground state compound that has 18 electrons.
Wouldn't that be argon?
Perfect, right? So we got argon, but if you think about it, chlorine minus and K plus or potassium plus, those ions also have 18 electrons, right? So how do we determine the atomic size from there? Well, because they have the same amount of electrons, we have to do something else. And remember how there are two parts of two charges within a molecule. There is a positive charge and the negative charge. The electrons deal with the negative charges and the positive charges deal with the protons. So because they all have the same amount of electrons, that means we move on to the protons and see how much protons are pulling within these 18 electrons, right? So we see that argon has 18 electrons, or 18 protons, chlorine has 17 protons, and potassium has 19 protons, right? And remember that there are 19 protons directly in the middle. Don't have this example, but there's 19 protons, 19 protons in the middle, which means there are more charges pulling inside. So that's going to make the atomic or the atom size squeeze in just a little bit further, right? And how we actually find this out is due to something that we call effective nuclear charge. And so basically that's saying if argon looks like this, it's a 3-shell thing, and it's got these full electron shells, and then, yeah, you guys know how argon looks like, right? So the way we calculate effective nuclear charge is that we would subtract, we would have our number of protons in the middle, then we would subtract how many electrons that are not the outermost electrons, right? So we got 2 electrons in here that would make up the second subshell or the first subshell. Then the second subshell is made up of 10 electrons. So, or 8 electrons, so for a total of 10 electrons. I'm sorry, I'm botching this explanation up, right? But there are 10 electrons that are not on the outermost shell. And so we would just subtract those. So that's 18 minus 10. Our effective nuclear charge would be 8. And then if we look for something like potassium, our effective nuclear charge would not be 8, it'd be 9. And so now we see that there's 9 forces acting among these 8 electrons, which means it's going to pull it in just a little bit further. So effective nuclear charge is pretty important, and that's how we actually kind of determine the atomic size with ions. Does anybody have questions on that? So just remember, subtract the number of protons minus the number of electrons that are not the outer shell. So because we have 2 complete subshells in there, that's that 2 minus the 8 in the second energy level equals 9. That's where I'm getting the 8, 9, and then for chlorine, we would see that the effective nuclear charge would be 7. And then the more charges that you have, the smaller the molecule.
Is this to compare atomic radius of ions?
Yes, of ions only.
Okay, another quick tip for that one is if they're all electronic, is that the one where they have the same electron configuration? The higher the atomic number, the smaller the radius. Just FYI.
Why? Because the effective nuclear charge increases. But yeah, that's a quick way to think about it. We good? Okay, that wraps up for module 12. If you guys don't have any questions, we will move on to the harder modules.
I'm gonna stop recording for my